Seni duymuyorlar galiba, beni duyuyorlar sadece. Okay. So, the subject is ring theory. Let me first state where the ring theory stands in algebra. In algebra, we have group theory, groups, and semigroups, and so on, other things. Rings and fields. This is our subject, rings and fields. Modules and vector spaces. And then we have other algebras. Like Lee, Jordan, and standard algebras, etc. Of course, we have other subjects, of course, but other exotic structures, like ternary rings and so on. Here we have near fields. Also, if you want to, near fields can be here or here. And okay, and these are the objects. This is the main area of interest. If you want to understand modules. These are the spaces in which we live. For example, three-dimensional space, for example, is a vector space. And rings and fields, they are like adjectives. Like 5, yellow. But but here we have you can add adjectives and you can multiply them. Here we have two operations. And groups are like transformations. Permutations. Like and the energies. They transform like winds, like rotation. Rotation. Translation. Translate something. Translation. Or symmetries. Things like this. There are movements. They move things. They move the objects. These act on objects. Acting on objects. These objects can be sets even, or they are more often modules and vector spaces. And the adjectives, they are like multiplying a vector by 2. Okay. Or by -1, the other side. This is the main object of study. And this is the course of which day? Tuesday's course. And these are necessary to understand these. Rings and fields are necessary to understand these. This is our subject, rings and fields. So what's a ring now? Let's say 1, chapter 1, definition. A ring is a structure of the form R plus times 0 and 1, where R is a set. R is a set. This is R. Set. Plus is a binary operation. On R. Times also is a binary operation on R. This means that if you have two elements here, R1 and R2, you can add them, R1 plus R2, and you can also multiply them. They are still here in R, not outside. They are inside R. So it's a binary operation. Binary operation means that you need two elements to operate. For example, taking the square is unary operation. You need only one. Take x squared. To add, you need two, x plus y. Zero and one are two elements of R, such that here I will write what I need by a ring. We will have 7 or 8 axioms. I forgot. They're called axioms. They are axioms really, but they're axioms of ring theory if you want to. It's a definition of ring theory. Such that. First, about addition. Let's say A1. X plus y plus z is equal to x plus y plus z. This is called associativity of addition. It's very important. This is very important. And this is more difficult to satisfy than other axioms about addition. A2, x plus 0 is equal to 0 plus x is equal to x. In other words, 0 is the neutral element. Neutral element. Etkisiz eleman Türkçesi. Of addition. A3 for all x, there is a y such that both x plus y and y plus x are equal to 0. So this is called the inverse of x. We show it's unique. Such is called a group. So in other words, R plus 0 is a group. So I've said nothing about multiplication here, only about addition. Addition and 0. Addition and 0. Nothing about about multiplication. In a group, this y must be unique. Let's say lemma 1. By the way, this 0 and 1 are not 0 of that we know, and it's not supposed to be necessarily. 1 is not a number. They are just called elements. They are just elements of R called 0 and 1. Lemma 1. Given x in R, the element y of A3 is unique. Bir tane var bunun. This y is unique. Given x, there's a y, and this y is necessarily unique. Why is this? In fact, more is true. or is to lemma 2 in a structure that satisfies A1 and A2, left and right inverses I will tell what I mean by this. Of an element X are equal X, if they exist, of course. This means that suppose A1 and A2 hold, suppose this hold. Suppose you have a right inverse and a left inverse. By left inverse, I mean Z plus X is equal to 0. By right inverse, I mean X plus Y is equal to 0. And by this, I mean X equal to Y. Z equal to Y. If the left inverse exists and the right inverse exists, then they're equal. Z equal to Y. Why is this? It's one line. It's only one line. Because Z is equal to Z plus 0 by A2. And this is equal to Z plus 0 is X plus Y. This is hypothesis H. And now associativity A1 is equal to Z plus X plus Y. But Z plus X is 0 by hypothesis. 0 plus Y. And 0 plus Y is Y by A2. So Z is equal to Y. And lemma 1 follows from this, because if you have X plus Y equal to Y plus X is equal to 0, that means that Y is both right inverse and left inverse of X. So therefore, if you have X plus Z equal to 0, for example, because of this and this, let me see, yes, because of this and this, Z is equal to Y. Since this element Y is unique, we can give a name to it, a special name to it. It's unique because such a Y is unique. It depends on X, of course, and is denoted by minus X. It's called the additive inverse of X. Lemma 3 so I have both three axioms now. So in a structure satisfying A1, A2, A3 minus X is equal to X. So this minus X is the inverse of X. Note that Y is equal to minus X if and only if X plus Y is equal to 0. If and only if Y plus X is 0. right? Because this means that -x is the inverse of x. And so y is the inverse, left and right, both, doesn't matter. So y is the right inverse, y is the left inverse of x, and y is 0 minus x. They're all the same thing. In other words, you can take here from here, you can take x to the other side. You change the sign, of course, -x here also. So -x, the inverse of the inverse of x is x itself. Why is this? Lemma 3. Proof. We have, first of all, x plus -x is 0, of course. Right? -x is the inverse of x. And -x plus -x is also 0. Yes, it's also 0. Because -x is by definition the inverse of -x. So x is the left inverse of -x, and -x is the right inverse of -x. You see, you add -x to the right of -x, you get 0. You add x to the left of -x, you get 0. But by lemma 2, let's write like this, lemma 2, by lemma 2, they're equal. X is equal to -x. Some students say, oh, it's very easy because minus is plus. This is nonsense. This is the proof. This is the correct proof. The other proof is wrong. It has no meaning at all. Okay. I continue with the axioms. You see, in a group, you can simplify also lemma 4 in a group. One can simplify. In other words, if x plus y equal to x plus z, then y equal to z. What do you do to prove this? You add both sides to the left -x. And if y plus x is equal to z plus x, so you can simplify from left and right also. Then y equal to z. If x plus y equal to z plus x, normally you cannot simplify unless the addition is commutative. But in general, in a group, the addition is not commutative. But in this case, A4, the addition will be commutative. A4, x plus y equal to y plus x. For all x, for all y. Here also for all x, for all y, for all z. Here for all x. If I say nothing, it means for all x, for all y. So this is an abelian group, or sometimes commutative group. Okay. So in a ring, this will imply that since z plus x is equal to x plus z, you can simplify y equal to z. This is in a ring, in a commutative ring, in a commutative group. This is about addition. A for addition. A1, A2, A3, A4. Now about multiplication. M1. Again, associativity. X times YZ is equal to XY times Z. This is associativity of addition. This is associativity of multiplication. M2, x times 1 is equal to 1 times x is equal to x. This is associativity of addition. Of multiplication. This is 1 is the unit or identity element. Or 1 of R of the ring is the unit identity element for multiplication. M3 may not hold. M3 may not hold. M3. It's not true that every element has a multiplicative inverse. X times y, there may be no y such that x times y is 1. M4 also may not hold. It may not be commutative. M4 may not be commutative. This is about multiplication. That's all for multiplication. Now I need an axiom for both that involves both addition and multiplication. This is called distributive law. X times y plus z is equal to xy plus xz. And the other one, x plus y times z is equal to xz plus yz. And one more, I will call this star. I want 0 different from 1. Okay. These are the axioms of ring theory. By the way, this is called a ring. Such is called a ring. This is a ring. In math, there's only one definition of groups, for example, for groups. There's only one definition. Everybody agrees about what a group is. But about rings, there are several definitions. There are several definitions. Of rings. It depends on your interest. This is the most popular one. This is what I will adopt. This is R definition. R definition of a ring. Some people, for example, they don't take M1, for example, M1, but they take something similar to M1, not this M1. Some people, they don't agree. They don't want to have 1, for example. And some people don't want 0 different from 1, sometimes for some reason. Any questions? You can ask your questions orally. Sorularınızı sorabilirsiniz.
Someone said, I had a really hard time proving the distributive property of multiplication in your analysis one book, I remember.
Analysis one book is something else. What is it? Is it? But this is in analysis one, it's an axiom.
Yeah.
In analysis one, it's axiom. It's given as an axiom. There's nothing to prove of. In set theory, maybe you can prove it, but you may want to prove it. But in analysis, it's one of the axioms of real numbers. These are not. There's nothing to prove here. These are just. This is just definition. This is definition of a ring. By the way, this A4 is a not A4. Sorry, not A4. Yes, A4. Yes, A4. A4 is a consequence of other axioms. Let me prove it if you want to. Lemma 4. A4 follows from the other axioms. A4 follows. This one is a consequence of the others. Why is this? Proof. So let X and Y be in R in a structure that satisfies all the axioms, maybe except maybe A4. Let X and Y in R. Now compute 1 plus 1 times X plus Y in two different ways. One way is the following. 1 plus 1 times X plus Y. I use associativity. So let's say I distribute from the right. This is 1 times X plus Y plus 1 times X plus Y. I distribute from right to left. Okay. And this is equal to X plus Y plus X plus Y. I don't, you see, these A1 and M1 tells us that in adding and in multiplying, you don't need parentheses. Right? That's right. It's somewhere here. Here maybe. A1 and M1 tell us that in adding and multiplying, we don't need parentheses. Paranteze ihtiyaç yok. Kaldır bunun yerine x artı y artı z yaz parantezsiz. Bunun yerine x kere x kere y kere z yaz parantezsiz. Neredeyiz? Bu da parantez. I don't need parentheses here. Normally I should have parentheses here and here, but there's no need to it. And another way of multiplying. Now use multiplication from left. Distributivity from left. Is equal to 1 plus 1 times x plus 1 plus 1 times y. Now distribute this. It's 1 times x is x, of course. 1 times x is also again x. Now y, and again y. So this is equal to this. Simplify x's. Simplify y's. You get y plus x equal to x plus y. Simplifying. This is the simplifying. We get x plus y equal to y plus x. So this is for free. This axiom is really for free. You don't need to put it there. It's a consequence of the others, of these laws actually. What else? Lemma 5. In a ring, x times 0 equal to 0 times x is equal to 0. 0 is, how do you call this? How do you call this 0? Like this. It is, it absorbs. It kills everything. Proof? Let's say, It's also almost one line. 0 times x is equal to 0 plus 0 times x. 0 times 0 plus 0 is 0. You see here. Here, if you put x, you take x equal to 0 here, 0 plus 0 is 0. And this is equal to 0 times x plus 0 times x, distributed law. And this is equal to 0 times x plus 0. This is what? This is A2. This is also A2. This is distributed law from right. Now in a group, you can simplify. This equal to this. Simplify 0 times x. Simplifying. We get 0 equal to 0 times x. And similarly, x times 0 is equal to 0. Lemma 6. In a ring, minus 1 times x is equal to x times minus 1 equal to minus x. How do you prove this? Again, one line. Proof. So I do 0 is equal to x plus minus x. No, sorry. 0 is equal to 0 times x. I know this from lemma 5. 0 to 1 plus minus 1 times x. You see, what's the definition of minus 1 in a ring? Yeah. For every x, I have a minus, right? This is the additive inverse of 1. It's minus 1 is the additive inverse of 1. Now distributed law, 1 times x plus minus 1 times x. And this is x plus minus 1 times x. So when you add this and this, we get 0. Therefore, this is the inverse of x. Hence, minus 1 times x is equal to minus x. Okay. What else? These are the basic properties. Definition and basic properties. Okay. Any questions? Maybe I have to give examples also. I give examples. Z, integers, the set of integers, together with addition and multiplication, with the usual addition and multiplication. Rational numbers, with usual addition and multiplication. Real numbers, complex numbers if you know. Hamiltonians if you know. They are one inside the other. They get larger and larger. They're all rings with the usual addition and multiplication. And what else? This is one example. What else do we have? We have modular numbers. You may not know them, but 0 and z. Modular numbers. It doesn't matter if you don't know one of these examples. We see that. What else? If R is a ring, then the set of polynomials of X is a ring. What are the elements of this? They are of the form R0 plus R1x plus R2x squared plus Rn x to the n. Objects like this, these are the polynomials. Here, this is R0 to the x0 if you want to. This is R1 times x to the 1. But we don't write x to the 0. And instead of x to the 1, we write only x. You cannot have rational numbers here or something else. You must have positive integers, natural numbers. X to the 0, x to the 1, x squared. You cannot have square root of x. And you cannot have something on the denominator. You have got something else. Okay. I will give more examples of it. We will have much more examples. Many more. All these examples, in all these examples, if R is a commutative ring, what does commutative ring mean? Commutative ring means to these, if also xy equal to yx, then the ring is called commutative. Commutative ring. You see, these rings, they are all commutatives. They are all commutative rings. Non-commutative rings, they are not too difficult to find, but they are much rarer. I will give examples. I will give examples. Yeah, okay. So let's give 5 minutes break before I do more. And if you have questions, please do ask them. Ses şimdi mi açtı sesi? Ha, kapatmış sesi değil mi? Sesi kapatmıştım daha önce. Ha?
Evet, kapatmıştım.
Ha. Evet. Gelelim ikinci kısma gelelim. Some computations. Some computations in rings. Now, suppose we are in a ring and we want to compute something like x plus y plus z times a plus b, say. So we can use the distributive law. This can be both sides if you want to, either one. This will be x plus y plus z times a plus x plus y times x plus y plus z times b. So this is distributive from left, and now from right. xa plus ya plus za plus xb plus yb plus zb. We'll have 6 terms. Here we have 3 terms. Here we have 2 terms. If you multiply x plus y plus z plus t with, say, a plus b plus c, we'll have a sum of 4 times 3, 12 terms. If you multiply x plus y plus z plus t times a plus b plus c times u plus v plus w, we'll have a sum of 4 times 3 times 3. What is this? 9, 36. Sum of 36 terms. Okay, this is easy, of course. Now, suppose we have something like this. Suppose we have x plus y plus a plus t times a plus, you see, in general, when we multiply, let's say we multiply in a ring sum of xi's, I of the finite sum, of course. In a ring, you can only multiply, add finite many terms normally. In order to add infinite many terms, you need some convergence. So this is I going from 1 to n, say. You multiply this with something else, yj, j going from 1 to n, 1 to m. What do you do? Like in here, you take one term from here, you take one term from here, so y times c, z times b, x times a, and so on. And you add them. You multiply these terms, and then you add them. This will be equal to sum of xi times yj, I going from 1 to n, and j going from 1 to m, of course. Right? Now suppose that here this is equal to a, and this is equal to x, for example. X plus y plus z plus z a plus t times a plus b plus x. Now again we'll have 12 terms. We'll have xa, ya, a times a times a is denoted by a squared, t times a, and then with b's, x times b, and so on. But at some point we'll have also ax, right? This and this, ax. We have xa in the beginning here, xa, and at some point we'll have ax, and in the end we'll have tx, or whatever. things. You see, this term and this term, normally, well, we cannot say that they are equal, but they may be equal. These terms may be equal. They are not necessarily equal, but they may be equal. In a commutative ring, they be equal. For example, let us do x plus y times x plus y. In other words, x plus y squared. Now we'll have 4 terms. 3 times 2, 6. 4 times 3, 12. 4 times 3 times 3, 36. Now here, 2 times 2, we'll have 4 terms. X times x, that we denote by x squared, plus yx. You see, to multiply, you take one term from here, one term from here, one term from here, and you multiply them in this order. And then you add them. You have 4 choices here, 3 choices here, 3 choices here. You get a total of 36 choices. Here we have 4 choices. Yx plus xy plus yy. In other words, x squared plus yx plus xy plus y squared. This holds in all rings. In all rings, this is true. But if the ring is commutative, or if x and y commute with each other, if xy equals to yx, then these terms are equal. X squared plus 2xy, we write 2xy means 2 in a ring means 1 plus 1. 2xy plus y squared. Is it 2? What's 2 in a ring? In a ring, 2 is equal to 1 plus 1. That's how it's defined. I should have given here a more sophisticated example, maybe. I give this as homework. Let x be a set. Let R be Q of x, the set of subsets of x. Define addition for A and B in R. Define addition A plus B. Normally it's denoted by A delta B. This means the symmetric difference. This is A union B minus A intersection B. Or if you want to, this is A minus B union B minus A. It's called symmetric difference. If A is here, is a subset, B is a subset, A delta B is the elements which are in A but not in B, and the elements which are in B but not in A. And define multiplication A times B to be A intersection B. And define 0 to be, I believe, empty set. Yes, empty set. And find 1 to be X itself, everything, the universal set. So here we have addition, multiplication, 0 and 1. These satisfy all these axioms. This is a ring. These turn R, the set of subsets of X, into a ring. I can give more examples. I can give more examples. Z add to its square root of 2. This means the elements of the form A plus B square root of 2, such that A and B are in Z. Under usual addition, these are real numbers, of course. You can add and multiply them with each other. And this is a ring. Q of square root of 2, this is also a ring, where you take the coefficients A and B now, not from Z anymore, but from Q. A plus B square root of 2 such that A and B are in Q. These are all rings. You can have others. You can take Z square root of 2 square root of 3. What's this? This is equal to A plus B square root of 2 plus C square root of 3. I need to multiply this also. Plus D times square root of 6. Where A, B, C, D are in integers. Other examples, you can take Z and then cubic root of 2. A plus B cubic root of 2 plus C cubic root of 4. You don't need 8, of course. But A, B, C are in Z. These are also rings on the additional multiplication. These are all commutative rings. I have only given examples of commutative rings. Oh, commutative. I can give a non-commutative. This is a non-commutative ring. This is a non-commutative ring. This is commutative. These are all commutative. This is non-commutative. What's the definition? This is equal to the elements of this are of the form. One element is of the form A plus BI plus CJ plus DK of this form. And when you multiply them, A, B, C, D are real numbers. When you multiply them, A, B, C, D commute with everything. I square, J square, K square, they're all minus 1. Ij is K, Jk is I, and Ki is J. This is called Hamiltonians. In honor to Hamilton, who discovered these numbers. This is very interesting ring. Non-commutative, you see, because Ij is K, but Ji will be minus K. You can check this. It's minus K. Kj will be minus I. Ik will be minus J. You see, Ij is not equal to Ji. Ij is not equal to Ji, but they are not too different. We'll get more non-commutative rings later on. Okay, let's come here. Now, suppose I want, this is if x, y equal to yx. X plus y cubed is x plus y, x plus y, x plus y. So I will have 8 terms. Yeah, I will have 8 terms. You choose one of these two, one of these two, one of these two. You multiply them and then you add them. You'll get x, x, x, choosing x only, plus x, x, y, plus x, y, x, plus x, y, y, plus y, x, x, plus y, x, y, plus y, y, x, plus y, y, y. I get 8 of them. 1, 2, 3, 4, 5, 8. 8 of them. I have 8 different terms. Of course, this is x cubed. This is x cubed. This is x squared y. This is xy squared. This is yx squared. This is y squared x. And this is y cubed. Normally, it's possible that none of these terms are equal to each other. They may all be distinct. And there's no reason a priori for them to be equal. But if xy equal to yx, then, for example, this term, and this term, they become equal. This is if xy equal to yx, x cubed plus 3x squared y. By 3, I mean 2 plus 1, of course. Or 3 times, you add x squared y 3 times. Plus 3 times xy squared plus y cubed. You may know the formula for these ones, but for example, what about if you do x plus y plus z to the third? What do you get? Here we get 27 terms. 3 times 3 times 3, 27 terms. But if xy equal to yx, and if xz equal to zx, if they all commute, you will get less terms, but with more. Here coefficients are 1. You have 1 here, always 1 here. Everything. But here you have 3 coefficients. Also, so 1, 3, 3, 1. It's 8 again. You see, you have 8. You have 8 terms, but some terms are equal. If x, y, z commute with each other, what do we get? Well, we'll get, first of all, x cubed. We'll get x cubed, right? We'll get x cubed. And we'll get y cube also, z cube also, right? So you have 3 parentheses. This is equal to x plus y plus z, x plus y plus z, x plus y plus z. You choose x from each of them to get x cubed. You choose y from each of them to get y cubed. You choose z from each of them to get z cubed. But now you have others. You have x squared. For example, you have x, y, z's, or x squared y's. You have x squared y's. How many x squared y's do you have? What does it mean? You have to choose twice x and once y. Right? You can choose x, x, y, x, y, x, y, x, x. You have 3 possibilities. Again, of course, the same with others. 3 x squared z plus 3 xy squared plus 3 xz squared plus 3 xy squared plus 3 x squared y. That's it, right? Right. And then we have x, y, z. So you have to choose x from here, y from here, z from here, or y from here. X. How many possibilities? We have, of course, 3 factorial, right? From here, you can choose you have 3 possibilities to choose from here. And then here, you have left with only 2, and here with only 1. Plus 6 x, y, z. I should have the sum should be 27. 1, 2, 3, 6, 9, 12, 15, 18, 21, 27. 27 terms. What about if I do x plus y plus z plus t to the 6? I will have 4 to the 6 terms. But if x, y, z, t commute with each other, then I will have less terms, but with higher coefficients, of course. The sum of the coefficients, again, will be 4 to the 6, whatever it is. Let us try to do this. A plus b. This is not x, y, z, t. Let's do a plus b plus c plus t plus d to the 6. Of course, I will have a to the 6, b to the 6. These are easy, right? You choose a to the 6 plus b to the 6 plus c to the 6 plus d to the 6. And then you will have, for example, ab cubes. AB cubes. How many of them? Of course, you'll have the same number with AC cubes, right? DC cubes, all the same numbers. Right. There are several of them. Yeah, they're all the same. And then we have some number of ABC squares. Things like this. If A, B, C, and D commute, of course. With the same coefficient, you'll have others. And then what do you have? We'll have a squared, b squares. And others like a squared, c squares, and so on. And then you will have a, b, c, d's. Right. Yes. So what are these coefficients? Oh, no, I'm sorry, this is 6. I'm sorry. I did this. Yes, let's do it 4. Sorry, 4. Let's do 4. Six is too much. So what is this? This is, you have to choose, you have 4 parentheses. You have to choose distinct letters from each. You can, from the first parenthesis, you have 4 choices, and then 3, then 2, then 1. So here it's 4 factorial. This is easy. 4 factorial. What about here? A squared, b squared. You have to choose 2 a's and 2 b's. Right? This, in fact, this is the number of, this number here, this is the number of anagrams of A, B, B. Yeah. In how many ways? It's like Scrabble. You have A, B, B. In Scrabble, in how many ways you can arrange A, B, B? You have A, B, A, B, A, B, B, A, B, A, B, A, B, B, A, A, B. Alphabetically, B, A, B, A, and then B, B, A, A. 6 of them, because I have 4 places, and I have to choose where to put 2 A's. But this is 4, choose 2, right? It's 4, choose 2 here. Here also 6. Here also 4, choose 2. Here, so the anagrams, number of anagrams of A, B, C, C. Number of anagrams of A, B, C, C. Well, I have to choose, for A, I have 4 places. For B, there are only 3 places left. And then you put, it's 4 times 3, 12. AB cube, the anagrams of A, B, B, B. You only have to choose the place of A. Yeah, 4. This is a 4. In general, how can you find the coefficients? Suppose I'm doing in a ring, I'm doing A1 plus A2 plus AK to the n power. And suppose that I'm in a commutative ring, or that AIs each commute with each other. So, do you have any questions? Kaç kişi var? Suppose I'm doing this. So this will be what? This will be sum of things, right? Sum of things. So, and you'll have some coefficients, and you'll have here A1 to the K1, for example, and then A2 to the K2. Fine, not K, let's say I1, I2, AK to the IK. And of course, the sum of these, I1 plus I2 plus IK, the sum will be n, this coefficient, this power here. And here I will have something. What is this number? What's this number? Well, this is the number of words written with I1 many A1s, I2 many A2s, and IK many AKs. Like in here, I have to count here number of words written with 2 A's and 2 B's. These are the words with 2 A's and 2 B's. I suppose, for example, I have A, B, C, D. How many words can you write with these? What is the number of anagrams? Anagram means that you just switch the places of letters, like in Scrabble. Suppose you have 4 A's, 3 B's, 2 C's, 1 D. How many words can you write? Not meaningful, of course. Well, how can you do this? Well, there's one way. First of all, how many places do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 places. I have 10 places like this. 4, 5, 6, 7, 8, 9, 10. From these 10 places, I have to choose 4 A's. It's 10 choose 4. Right? So you put A. And once you have chosen these 4 places for A's, you have 6 places left. And from these 6 places, 1, 2, 3, 4, 5, 6 places, you have to choose 3 B's. 6 choose 3. And now, suppose you have chosen 3 B's. Now you have 3 places left, right? 1, 2, 3. You have to choose from these 3 places, you have to choose 2 C's. Here and here, for example. And then finally, you have 1 place left. And this is 1 for D, right? In general, how do we do with this? I have n places. Çekiyor musun? Gözüküyor mu burada? I have n places. 1, 2, 3, 4, 5. N places like this. I have to choose the places to put A1. So this is n choose A1. So once you place I1, sorry, I have to choose I1 many places to put A1s. Right? And now once you have put the A1s, I1 many A1s, what's left is n minus I1 places. And now you have to pick I2 places, put your A2s. Now, once you have put this, then you have left with n minus I1 minus I2 many places, and you have I3 places to choose, and so on. And until what? Until n minus I1 minus I2 minus I, k minus 1. Choose IK. If you do the computation, there will lots of simplifications. Look, for example, this one. This is equal to n factorial over I1 factorial over n minus I1 factorial. This one. And now for this one, n minus I1 factorial. See, there is simplifications. Over I2 factorial over n minus I1 minus I2 factorial. Next, you have this now. You have n minus I1 minus I2 factorial over blah, blah, blah. As you see, these simplify. And you will left with here n factorial on top. N factorial on top. There's only n factorial on top. At the bottom, we have I1 factorial, I2 factorial, I3 factorial. Those are the coefficients. If n equal to 2, if k equal to 2, they're called binomial coefficients, as you know. Binomial theorem is called something. If k equal to 3, you can call it trinomial coefficients. This is denoted by n choose I1, I2, IK. How this is denoted somewhere. It is astonishing fact that this number is an integer. It looks like as it is here, it looks like a rational number, but everything simplifies. For example, take n equal to 25 factorial. Here take 12 factorial, 6 factorial, 18, 3 factorial, 21, and 4 factorial. You see, we know that 12 factorial divides 25 factorial. It's easy. This also divides, this also divides, this also divides 25 factorial. But the product divides 25 factorial is not trivial at all. It's astonishing. There's a theorem here. Theorem. If I1 plus I2 plus IK is n, then I1 factorial IK product of these factors divides n factorial. So this is in all commutative rings. In all commutative, this formula, right? Holds in all commutative rings. Soru var mı? Saat kaça kadar ders? 12:40 mıydı?
12'ye kadar.
12:40'tı sanki. Orada birileri var mı dinleyen hala?
Buradayız hocam.
Ha, iyi.
Dinliyoruz hocam.
İyi. Her şey yolunda gidiyor mu?
Güzel gidiyor şimdilik hocam.
Aynen.
Hı.
Anlaşılır hocam şu an.
Efendim?
Anlaşılır vaziyette iyi gidiyor hocam.
İyi. Yani ses çıkan arada bir anladık anlamadık falan bir şeyler söyleyin. Peki. Bir 5 dakika daha ara verelim. Fazla değil ama 5 dakika. Haftalar doldu. Oradan devam edelim.
Çok da iyi geliyor.
Nasıl? Nasıl görüyorsun? Ne yaptık? Bir, definition and basic properties. Two, some computations in rings. And three, now, polynomials and power series. Let us start with polynomials. So a polynomial is something of the form. First of all, let R be a commutative ring. When you speak about polynomials, R must be a commutative ring. Be a commutative ring. And a polynomial is something of the form A0 plus A1x plus A2x squared plus up to some place, an x to the n. If this is non-zero, and this is the last coefficient is non-zero, n is called the degree of the polynomial. But if n is zero, then the degree is less, of course. If they are all zero, if it's zero polynomial, then degree is said to be minus infinity. Degree of the zero polynomial is said to be minus infinity. Otherwise, degree of a polynomial f, if it is non-zero, it is the maximum n d, maximum d such that if this is f, such that the d coefficient is non-zero. So let's take a polynomial and multiply it with some other polynomial. B0 plus B1x plus B2x squared and so on. First of all, adding polynomials is very easy. Adding polynomials is very easy. Adding polynomials, just add the coefficients. A0 plus B0 plus A1 plus B1 times x plus A2 plus B2 times x squared and so on. You add coefficients, the corresponding coefficients. Multiplying is more complicated. See, how to multiply? We know how to multiply in a ring. Let's write this like sum of AI x to the i's. I from 0 to n. And let's write this as bj x to the j. J from 0 to n. Let's write this like this. This n and m are disturbing. These are disturbing. Disturbing. You can continue this up to infinity plus 0 times x to the n plus 1 plus 0 times x to the n plus 2 and so on. Keep going like this. Add zeros. And here also you can put plus 0 times x to the n plus 1 plus 0 times x to the n plus 2 and so on. Go as far as you can up to infinity. So like this is I going from I, all i's. AI x to the I times sum of bj x to the j's, so for all j's. Now we know how to multiply two entities like this. We have seen here. There was an important formula here. Here it is. Let's do this red also. How do you multiply things like this? You take one term from here and one term from here, and you add them all. You multiply them and you add them all, right? It's very simple. Here, if you want, you can do like this. Sum of xi's for some i's, doesn't matter, it goes from 1 to n. And sum of yj's for all j's is equal to sum of xi yj's for all j. It's a very simple formula. Here, how do I multiply this? I take one term from here, one term from here. I multiply them, and then I add them. This will be sum for all I and j, ai x to the I. I took this term here, and I will take this term here now, bj x to the j. Okay? This is distributive law. Left and right distribution. Left and right distribution. Remember that these AIs are 0 after a certain point. BJs are 0 after a certain point. Now, we assume that the coefficients AI and BJs are from this commutative ring, from R. I will assume in polynomials that they will be commutative. BJ will pass from here. Okay, this is the coefficients R, the elements of R will move from right to left. This will be equal to sum over I and j, ai bj times x to the I, x to the j. This is a multiplication in R. So now I have to multiply these two. I have to multiply x to the I times x to the j. If you agree that x to the I is I times x multiplied, if x to the I is equal to x times x times x times x, I many, then this will be j many x's here. This will be, of course, then sum of ai bj x to the I plus j. For all I, for all j. Right? This is, we assume that x to the I is equal to x times x times x. I many. You see, let's take this I from top to below. Now it's not anymore, it doesn't mean anymore x to the I. It's not anymore multiplying x with itself I times. Now we'll have, see, now we'll have this ij. Now you'll not have this anymore. Not necessarily, you know. This xi is something else. You don't know what it is. It's something else. But it will be something. I'll assume now, let's for the moment assume that this is just power. Multiplying x with itself, and this is multiplying x with itself j times. Okay. Let's assume this for the moment. Now, let's continue. This is for all I and j. You see, for example, I plus j can be equal to 5, say. I plus j can be equal to 5, but it can be equal to 5 many times. I can be 0, j can be 5. I can be 1, j can be 4. I can be 2, j can be 3, and so on, right? So let's put them together. The sum, x to the k. Let's call this k. And this is for k. Sum over k. Here we'll have a coefficient here. What will be the coefficient? It will be ai times bj, a sum of ai times bj's, but I plus j must be equal to k. Right? This is the multiplication in polynomials. In other words, when we multiply these, I will get a0, b0. This is called the constant coefficient. Next, for coefficient of x1, x to the 1, x, you'll have a1 times a0 times b1. A0 times b1, you see this and this. And then a1 times b0. What about coefficient of x squared? a0 b2 plus a1 b1 plus a2 b0 x squared. With x cubed? Yeah, you see, the sum of the indices must be 2 here. Here, the sum of the indices will be 3. A0 b3 plus a1 b2 plus a2 b1 plus a3 b0 x cubed, and so on. Right? Now let us think 1 second. You see, I can have more terms here. This a0 b0 depends only from the coefficient, this coefficient a0 and b0. In order to perform this multiplication for the first coefficient, I need only the first coefficients of a0 and b0. In order to compute this, I need only this small part of the polynomial, the first 2 terms. To compute this, I need the first 3. I need the first 3, this and this. What does it mean? It means that I could go here forever. No, in order to perform the multiplication, I don't need to stop. I can put here plus, continue, an plus 1, x to the n plus 1, plus an plus 2, x to the n plus 2, and so on. Keep going, keep going. And also here, put bn plus 1, x to the n plus 1, and keep going. You can still do this multiplication. You can add also. I think it's very simple. You just add the coefficients. And the multiplying, it's still possible to multiply if you keep going like this. It's like multiplying 2 numbers. For example, let's multiply 3,216 and 2,547. When you multiply these two, you only need 6 and 7 here to guess. This is 42, this is 2, this will be 2. I know this will be 2. This may be 5, this may be 8, this may be 0, this may be 9. Doesn't matter. This will be 2 because this depends only on these 2. Now, in order to find the next number here, this digit here, you only need these. Doesn't matter. You may have 5 here, 8 here. Doesn't matter. This digit here will not change. This will 42, you have 4, 24, 31, 25. This will be 5. This will be 5. Right? Even if you have 9 here, 5 here, doesn't matter. You can go up to infinity if you want to. In order to compute this number, you only need these 3 digits. Find the amount of data you need. So the numbers don't have to stop in order to multiply them. They can go forever. I think it's the same. If you want to add 6, 7 is 13, right? 13. I only need these 2 digits. 13, and then next it will be 6. Doesn't matter what you have here. So even in numbers, you don't have to stop for natural numbers. You don't have to stop. They can go forever. You can still do multiplication and addition. It's another rank, of course. It's something else. It's something else. If you stop, they're called polynomials. If you go forever, it's called power series. Out of x, this is the ring of polynomials. If you go forever, then it's not like this double bracket. The ring of power series. This is inside this, of course. Each polynomial is a power series. You go forever, but these are zeros. After a while, in a polynomial, the coefficients after a while are all zeros. But in power series, you go forever. Let's see. Let's give some examples of multiplication in power series. No, remember, the multiplication is like this. AI x to the I, for I going from 0 to infinity. This and this, bj x to the j, or j. This is equal to sum over k, x to the k here. And here you will have a power, you have a coefficient. Sum of AI times bj, but for I plus j equal to k. Here, this is a sum of k plus 1 terms. For example, let us do this. Let's find a sum of, let's multiply this. 1 plus x squared plus x cubed and so on. Together with 1 plus x squared plus x to the 4 plus x to the 6 and so on. Let's multiply these things. Okay, and so let's find the coefficient of x to the 100. X to the 100. So you'll have what? X to the 100 here. What will be its coefficient? This coefficient will be AI times BJ's. So I plus J is equal to 100, right? If you want to, let's do like this. Let's do like this. Let's write this here. This is sum of x to the i's. I going from 0 to infinity. That's fine for all I. And the other one, it will be sum of x to the 2j's. J going for all j. Okay. So when I multiply these two, what do I do? I take one term from here and one term from here. Sum for all I and j. X to the I plus 2j. Now, this I plus 2j will be equal to k for several values of I, right? For several values of I. So this will be equal to sum over k, x to the k, and here I will have a coefficient. What will be this coefficient? This will be the number of solutions, the number of solutions of I plus 2j equal to k. Right? How many times I plus 2j is equal to k? Because each coefficient is 1, right? Yeah, multiplying once. Is this clear? Anlaşılıyor mu?
Yeah. Yes.
Okay.
Yes.
So the question is, so this is equal to number of solutions. Number of solutions of I plus 2j equal to 100. You know, in natural numbers, right? So, so here I cannot be 1 because otherwise, you know, 100 is an even number. This even number. I must be even. I can go from 0 to 4 even numbers up to 100. I guess we have 51 of them, right? So the answer will be 51. If you do, let's do this, for example, 1 plus x squared plus x cubed plus and so on. You multiply this with 1 plus, like this one here, x squared plus x cubed, x to the 4th plus x to the 6th and so on, even powers. And now let's take 1 plus x to the 5 plus x to the 10 plus x to the 15 and so on. We multiply that. This is equal to sum of x to the i's over I. This is equal to sum of x to the 2j's over j. This is equal to sum of x to the 5k's over k. When I multiply, I will get for all I, j, k, I will choose one term from here, one term from here, one term from here. X to the I plus 2j plus 5k. Right? And now, this will be what? So, this will be equal to L for several values of I, j, and k. For several but finite many values of I, j, and k. So, this will be sum over L, say, x to the L. And here I will have a coefficient. This coefficient will be number of solutions of I plus 2j plus 5k equal to L. Mathematics. I can give you a nice problem. For example, you can compute the coefficient of 100, x to the 100 coefficient. So you have two more examples of rings. They are both commutative. Let me give you an example of a non-commutative ring. I will do more about power series. This is very polynomials and power series are very important. Power series are easier than polynomials. Let me give you another example. Non-commutative this time. Some of them will be non-commutative. 4 group rings. Let us go back to the polynomials. Let's go back to the polynomials. I will be inspired by the polynomials. I will generalize the polynomials, the concept of polynomials. What do we do? Well, to add is very easy to polynomials. How do we multiply them? AI, bj, AI, x to the I, and bj, x to the j. This is equal to sum over INJ, AI BJ, x to the I times x to the j, okay? X to the I times x to the j. Okay. This is x to the I plus j, but forget about it. And defining multiplication like that, I get a nice structure. I get a ring, right? And addition is easy. Addition is just component-wise. Multiplication is somehow sophisticated, but if you write it like this, it's not sophisticated at all. You take one term from here, one term from here, and you multiply them. Okay. This is we get a ring structure. We get a ring structure here. So what do we owe the ring structure? Addition is simple. There's not to be addition. What is difficult in the ring structure is associativity. This associative one, x times yz is equal to xy times z. This is very difficult to obtain. Associativity is very difficult. Everything else is simple. You can get everything else very cheaply, very easily. But to obtain this is very difficult. In polynomials, this holds. Well, if you have f, g, and h, in polynomials we have this equality because we have this kind of equality at this level. Let me say, in polynomials, the associativity holds, the associativity of the multiplication, holds because the associativity holds at the level of x to the i's, i.e. x to the I times x to the j times x to the k multiplied like this or multiplied like this are the same. As I did before, let us forget that this is x to the I. Write this x to x sub I. Forget about what this. And this is sub j, and this is x sub I times x sub j. This could be anything. X to the I could be anything. Now, don't give any meaning to it. X to the I can be something absurd. Now, define multiplication like this. This will be associative only if x sub I, x sub j, x sub k multiplying like this. Only if the associativity holds at the level of these generators. I may call them generators, these things. This is very simple to check. If you have the associativity at the level of generators, then you have the total associativity. So forget about these x sub i's. Forget about that the i's are integers. Suppose G dot is an associated, is a structure where multiplication is an associative operation, binary relation, I would say binary operation. İkili işlem. Together with one, say. Well, do I need one? Well, maybe. Let's take it together with one. In other words, I have a G times hk is equal to gh times k, and 1 times g and g times 1 is equal to g. I don't even need inverses. Example, I can take g to be 1, x, x squared, x cubed, and so on. And multiplication, I define multiplication by x to the I times x to the j equal to x to the I plus j. In the case of polynomials, I have these. Now consider, and it is like this. Sum of a sub g times g for g in g. You see? Like this. So instead of xi's, I take g's, and I index the coefficients by a to the g, where a to the g and r is a ring, and r is a commutative ring. What's that? Things of the form. Formal objects. So this will be a1 times 1, and then ag times g, and then like this. So to add them, addition, sum of ag times g for g in g plus sum of bh, say, let's say bg again, bg, g in g. Addition is very simple. You add them as you get ag plus bg, this is in a commutative ring, bg times g for g in g. That's like g. Yeah? Addition is easy. Multiplication. I will have slight problem in multiplication, but I will correct it. Multiplication. Sum of ag times g for g in g times sum of bh times h for h. So I will multiply as before. So I will take one term from here, one term from here. I will multiply them, but I will decide that the b's, the coefficients, commute with the rest. So this will be sum over all g and h of something from here, ag times g, and bh times h. But bh will go before g. I will assume that bh commutes with everything. ag times bh, gh. That's correct. Right? Because it's a distributive law. I want this to be true. And then now this gh, this is in g, of course, these are elements of g. G is a structure closed under multiplication. This is in g. So I can write this as sum over k, for k in g, of course, k. And here I will have a coefficient. This coefficient will be the sum of these, of course. Sum of ag times bh for g times h equal to k. Okay. So the multiplication, if it exists, it should be like this. But there's a small problem here. I have a problem here. Is that this sum may be infinite. There may be infinitely many g and h such that the product is equal to k. Possible. For example, if you take here, let's take natural numbers. Now, I'll give this example later. You see, this sum, if it's not finite, you cannot compute it. It's impossible. You cannot add infinite many numbers, infinite many elements in a ring normally. So, how do I manage it? I can make sense of it. What's this? Because, let's write this, because gh equal to k may have infinitely many solutions. for a given K. For some K, this may have infinite many solutions, and then you cannot complete this. But if you take only finite sums, consider things of the form, of this form, but finitely many. Suppose you have only finitely many AGs here. The rest are zero if you want to. With finitely many non-zero AGs. By the way, here is a multiplicative structure. Don't take addition here, just multiplication. Because otherwise you will get confused. Once I was confused, I took addition here. Once when I was younger, much younger, your age probably, I took addition here and I get all confused. I thought there was a contradiction in math. Take a multiplicative structure. You know this with multiplication. Okay, now this makes sense. Now we have because we are choosing between AG and BH. Most of them are zero, so I think you can add infinitely many zeros. Doesn't matter. So this will have finitely many solutions. Now this will make sense. The structure called is denoted by RG. RG. This is equal to sum of RG, say RGG, where G and G, finite sums, finite sum, where RGs come from the commutative ring R, and G is only a structure. Is only a structure where with these two properties, it is the identity one. This is not even necessary, but let's take it. The one, and the most important is associativity of the multiplication. Then this is a ring. The set becomes a ring with the addition and multiplication. Defined above. If G is 1x squared with xi times xj equal to xi plus j, we get the polynomials. If G is, take x to the i's, for all I in Z, with the same multiplication. So now we have 1 over x, 1 over x squared, and so on. You have x to the minus 1, and so on. Then you get something else. I believe it's noted by, I'm not sure, or something like this guy. I'm not sure. You get another thing. But now, you see, you cannot take, you see why I took finitely many coefficients, non-zero coefficients. Suppose you are taking 1 plus x squared plus x cubed plus so on. And then here you take x to the minus 1 plus x to the minus 2 plus x to the minus 3. Suppose I took these elements also. Suppose I can say this. Now try to square this element. When you square this element, find the constant coefficient. You will get 1. And you will get twice this, right? Plus 2. And then you get twice this, plus 2. And then you will get twice this, plus 2. So you will not be able to compute it. Okay. What's funny is that if you want to, you can, if you stop from here, if you stop to the left, there's no problem. You can go to the right as far as you can. Or else you can do the converse. You can go to the left as much as you can, but you stop here. But you cannot go both ways to infinite. Because then you'll not be able to multiply them. Very often, we take for G a group. Very often, G is taken to be a group. Of course, you may regard G as a subset of this, right? Because an element of G is also something like this. Take all the coefficients to be 0, except the coefficient of G to be 1. So G is a subset. R also is in here. R also in here. It is constant. Take R. G has one here. Just take element R. You can see it is R plus 0 times G1 plus 0 times G2 and so on. Often G is taken to be a group, and in this case, R of G is called grouping. It's like polynomials. It's like polynomials, except that we don't have x to the i's. We don't have x to the i's. We have elements from a group. And these are formal objects. What does it mean by formal? I mean that, like, when do we have two polynomials are equal? If and only if the coefficients, the corresponding coefficients are equal. When do we have two grouping elements equal? If and only if the coefficients are exactly the same. The constant coefficients are the same. The coefficients of G are the same. The coefficients of H are the same, and so on. It's called a grouping. And of course, R of G is commutative if and only if G is commutative. Right. What?
You said that earlier GH is in G. So does that imply that H is also in G? We only said that G is in G.
When I say about G, H, K, and so on, I speak about the elements of G, of course. Where do you see H here? Of course, this H is from. Yeah, I can write also like this. Also, this is also true, of course.
Oh, okay.
But if you do this, then you will be mistaken in multiplying. So I change G into H. This H runs from G, of course.
Right.
So the G runs from G. Like in here, instead of G, I took H. Now, here, there's no G, in fact. You see G here, but this G is mistaken. Like, for example, what is this, for example? This is equal to A0 plus A1x plus A2x squared. And it goes. Do you see any I here? There are no I's here. Therefore, there should be no I here either. There's an I, you see an I, but this I is called muet in French. You don't hear it. You don't see it. It's a non-existent I here. This I that you see here is non-existent. It's not there, you see. It's only a tool to describe the element.
Okay, thank you. I got confused. Like, you multiply two numbers and they're in G. The result is in G, but you only said that G is in G. So
G and H are in G.
yeah, okay. Thank you.
This is G. G is in G. It's the definition of the elements. For example, if you take, let's take Z, let's take integers, Z of sim3. What are the elements of this? This is A0, A1 if you want to, plus A12, 12, plus A23, 23, plus A1313 plus A123 plus A132 132. This is one element. A typical element is like this. These numbers, these A's are integers. You can take all to be 1. Take them 1. 1 plus 1 plus 1 2 plus 1 3 plus 2 3 plus 1 2 3 plus 1 3 2, for example. If you call this X, prove that sigma times X, G times X is equal to G, is equal to X, sorry, is equal to X, all X for all G in sim3. Conclude that X squared is equal to 6X. Homework. I will give you another homework. Yeah. Suppose I have 100 liras. Turkish liras. And I go to the bank and I want change for it. So the bank has 1 liras, 5 liras, 10 liras, 20 liras, 50 liras, and 100 liras. In how many ways can the clerk there, can give me exchange? Yani parayı kaç farklı biçimde bozdurabilir bilirsin. Clerk give a change. For this compute the coefficient of x to the 100 in sum of x to the i's times sum of x to the 5j's, sum of x to the 10 cars or 10 liras, sum of x to the 20 l's, and sum of x to the 50 m's. This is enough. You don't need to forget about 100. Okay? Compute this. But do it in a clever way. Maybe I will do this next time. Interesting fact here. If you put AIs to be 1, if AIs all 1s here, you get some of these things, some of 1 over I1 factorial, IK factorial, such that I1 plus IK is n. is equal to k to the n over n factorial. Interesting formula. Right? Take all the AIs to be 1. Because you can get other formulas by choosing AIs to be different numbers, but they're not very interesting. Okay. How is it going? Is it easy, too difficult, too easy, too difficult? Or just as it should be?
Well, it is sometimes hard to understand. Maybe that's because we're first-year student. I am a first-year student.
You're a first-year student?
Yeah.
Where?
Here in Istinye University, Mathematics.
I see. But yes, first year, yes. You can understand it. It's not impossible. It's not impossible. Maybe you don't know what a group is, of course. But this course is not designed for you. You know this.
Yeah, right. Actually, Miss Mahmoud Cepolu sent us the link. You know, if you guys want to attend the class, you can.
I see. Okay.
I wanted to see.
Others, are there any other first year students there?
Me too, sir.
I'm
a first year student, yes.
Okay. But you are not taking the class officially, right?
No, we're not.
You are just here for curiosity. Okay, it's fine. It's fine. Okay. Then see you next time. Next time means what?